Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 2.40. A solution containing hazardous waste is charged into a storage tank and subjected to a chemical treatment that decomposes the waste to harmless products. The concentration of the decomposing waste, C, has been reported to vary with time according to the formula. And then they give us a formula. The formula is this. When sufficient time has elapsed for the concentration to drop to this level, so C final equals 0.01 grams per liter. The contents of the tank are discharged into a river that passes by the plant. The following data are taken for C and T, and then they give us a table of values. So the table T, okay. If the given formula is correct, what plot would yield a straight line that would enable you to determine the parameters of A and B? Okay, so there are a few different plots that we could do. One that comes to mind is just to take the reciprocal of this. So the reciprocal of the function that we were given is equal to A plus BT, and this looks a lot like a line. So so if we have our formula, y equals mx plus b, then I would say that y equals 1 over c, x equals t, m equals b, and b equals a. Yeah, this formula, that's it for part A. This would allow us to determine what those parameters are. Okay, estimate A and B using the method of least squares, appendix A.1. Check the goodness of the fit by generating a plot of C versus T that shows both the measured and predicted values of C. The measured and predicted, okay, yeah. So predicted is the model, basically. So this is the model. So those would be the predicted values. And then this is the measured values that they gave to us. So we'll plot both of those. And once we've calculated what A and B are, we can plot the data and the model on the same chart. Okay, so in the last problem, 2.39, I showed how you would calculate a line using Excel. And so I'm not going to use Appendix A like they suggested, because Excel does it way faster and it's just as accurate. So nobody really uses Appendix A method to do that anymore, because it would be like adding instead of doing multiplication. So if you had to do a multiplication problem and you did 4 times 3, it would be like writing 4 plus 4 plus 4 instead of just knowing that it equals 12. So we're not in the Stone Age here. I'm not going to use Appendix A. I'm going to use Excel to solve what A and B are. So let's shift over to the computer. I forgot to hit record when I was doing this voiceover portion, and so the computer won't match up with some of the explanation here, so I decided to just kind of voice this over. Right here we're entering in the table values, and then after that we'll plot the data and also create a smooth model using our parameters that we calculated. So here we've plotted we've created the table, and now we're creating our line. So y is equal to 1 over c, so we're inputting that. converting our data into the line model. So y is 1 over c, x is equal to t, and just dragging that down. And now we can calculate our parameters from the x and y data that we created. So slope is calculated from the data, the x and y points that we made, and now the intercept is being calculated. And then we can calculate, or we can convert the slope and intercept data into our a and b parameters that we were given in the problem. A is equal to the intercept and b is equal to the slope. Okay, now that that is done, we are going to create a smooth model. So we'll put in several extra points so that when we draw the line, it will be smooth compared to the data points, and it'll be easier to see what's the model and what's the data points. But we'll do it within the same range. So we did t increasing by 0.1 each step up to 5, and now we're inputting our model here. And our model is 1 over a plus b times t. And we don't want our parameters to change as we drag the formula down, so we'll do that. And then we'll drag the formula down. And that's our model there. So now we'll plot the model on with the data points. Right here I'm calculating what the model predicts when t is equal to 0. You can see that 1 over c is equal, or you can see that the model is equal to 12.1. Okay, here we're inserting the charts. We're entering in the data. C against T, so that is the data point there. And now we're entering in our model C versus T, the smoothed version has lots of extra data points. And now we can convert those data points into a line just by changing the format. So we're removing the markers and changing it to a line, and then changing the color to black so we can see it a little easier. And that is the plot that they asked for. So that's it for parts A, B, and then we'll do C back on the iPad. So we'll move back over there. Now we'll do part C. Part C, using the results of Part B, estimate the initial concentration of the waste in the tank and the time required for C to reach its discharge level. So what that means is we want to know the initial concentration. So we need to say, what does C equal, using our model, when time equals 0? And then we also want to know the time required for C to reach its discharge level. So we want to know what T equals when C equals 0.01 grams per liter. And this equals hours. Okay. So that's what we want to know. The first one's pretty easy. We just plug it into our model, what T equals 0. So we'll just put 12.2 about grams per liter. So that we just plug right into the model. We could solve this other one numerically, or we could just solve it algebraically in terms of T. So let's go ahead and do that. So right now we have C equals 1 divided by A plus BT. Now we can solve this in terms of T. Let's say A plus BT equals C, 1 over C. And then we have T equals 1 over C minus A divided by B. Okay. So then we put 0.1 in for C, and T equals 209.4 hours. Okay, that looks about right. You should have very little confidence in the time estimated in part C. Explain why. Well, you're extrapolating out to 200 hours, and you only have data for 5 hours. So that's quite a far extrapolation to make based on a small amount of data. So yeah, anytime you're extrapolating very far away from your data set, your estimate is going to be way off. So part E, there are other potential problems with the whole waste disposal procedure. Suggests several of them. Well, if you have the first thing that comes to mind is this a batch process, or is this a like continuous treatment? A solution containing hazardous waste is charged into a storage tank and subjected to a chemical treatment that decomposes the waste to harmless products. I guess it depends on how big your stream is. To have something sitting and not doing anything for 200 hours is like a really long time. So that seems infeasible to me to store something for that long. So yeah, that's my initial thought. It's like, is there something wrong with their process to have to store something for that long? Maybe there's a better way to do it so you don't have to store it. Or maybe you could do it so that it's not storage and you have like a continuous line of treatment or something like that. Some sort of scrubber or something like that. The other thing is they're dumping it into a river, so you have to make sure that there's environmental codes that you're following. So you have to make sure that that level, that concentration, 0.01 grams per liter, is a safe concentration to put into the environment. They don't really give us any information on that, but it seems like they have this process figured out, at least to a certain degree, where they're discharging at that level for some reason. So perhaps that is a safe concentration to dump it, but it depends on whatever the waste is, and they don't tell us what it is. So you have to make sure that that's safe. Yeah, those are two things I can think up off the top of my head as to what might be wrong with this process. Well, that is it for problem number 2.40. Thanks for joining me, and I hope to see you in the next video. Thanks.